So we've talked over the last few videos about drawing Lewis structures, and that gives us a general idea of how molecules are connected. But we haven't really talked about shape at all. And shape is actually very important in chemistry. So in order to talk about shape, we're going to use a tool called valence shell electron pair repulsion, which is as simple as it sounds. We're talking about valence electrons, and the bottom line here is electrons don't want to be near each other, so they repel each other. So they try to get as far away from each other as possible. So, for example, let's say that I have this hypothetical covalent compound. Now, I know it's not actually covalent, but if we said that it was, okay, then the Lewis structure for this would be something along the lines of VEFF. And we got lone pairs around here, and beryllium wouldn't need an octet because of it's in group 2 and would only have 2 electrons to share. So here's the problem. This is a pair of electrons here, and this is a pair of electrons here. And pairs of electrons don't want to be near each other. They want to be as far apart as possible. So I haven't actually drawn this correctly, right? It would be better for me to draw it like this. Okay, with my fluorines as far apart from each other as possible. And then this angle would be what? Be 180 degrees. And how would you describe this shape? I want you to just guess. What's the first thing that comes to mind? Well, it's kind of 3 points all along the same line. So maybe we'd call this linear. And in fact, we do. And I'm going to be using a modeling thing, which I'll put a link to in the graphical organizer that you can kind of play with. So here's a linear molecule, okay? You can see, I'll look right down that. The angle between those two bonds, those two pairs of electrons is 180 degrees. We said it's linear, all right? So that's BEF2, great. What about BF3? Well, BF3, so boron's another one of the exceptions to the octet rule. It can make compounds with 6 electrons, right? So here's boron, fluorine, 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 and then I'll fill in my lone pairs. Okay, so now I want you to think to yourself, all right, well, now instead of having 2 things connected, now I have 3. So what's the furthest apart that these things can be? Well, if I take this circle and I divide it by 3, I'd get 120. So these angles should be 120. And if I go back to my modeling program, okay, and I add a bond, you'll see that all the angles are 120 degrees, okay? So it looks like that. Okay, the name of this compound is trigonal planar because all the bonds are in one plane, okay? All the elements are in one plane. Okay. What about something like CF4? Okay, so I'll draw out my Lewis structure. And now, how far apart do you think these can get? And what kind of angles do you think we would have? How would you describe that shape? A lot of people will say that they think that this is 90 degrees. Do you agree? Hopefully not, because this actually turns out to not be the case. What we're forgetting is that we're not two-dimensional, okay? We're three-dimensional. And in a trigonal planar structure, the farthest apart that these things can get is 120 degrees, and that just happens to put them all in the same plane. If I try to take one of these atoms here and move it up, then you'll notice that that decreases some of the bond angles, and that's bad because that would increase the amount of repulsion. All right, but if I add another bond, now we have to take advantage of the third dimension, the sort of z-axis, right? So now you can see that all the bonds are equally spaced at 109.5 degrees, okay? And that's about as far away as they can get. Now, this shape is called tetrahedral, okay? And we'll talk about that in a moment. So, wouldn't you like to know how to name the structures for these and how to figure out what their shapes are going to be? Well, lucky for you, I'm here, and I'm about to tell you what's going down. So, here are our steps for getting a Vesper structure. And a Vesper structure is just, it gives you an idea about the shape of a molecule. And we'll use the example NH3, okay? And the first thing that you need to do is make the Lewis structure. Well, I know that the Lewis structure for NH3 looks like this. N, H, 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 with a lone pair there, and everybody's happy. Okay? The next thing that you need to do is you need to count something called the steric number. Now, this isn't in your textbook, but I think this is very helpful. Okay? Count the steric number. The number of quote-unquote things attached to the central atom. Now, that's either going to be bonds or lone pairs. It's basically like you're counting the pairs of electrons. So, around this central atom, which is the nitrogen, there's 1, 2, 3 bonded pairs and 1 lone pair. So its steric number is 4. Okay? Now, we figure out the base geometry, okay, the base structure, which is the structure of an atom with 4 other atoms attached. Okay? Lone pairs do some weird stuff, and we're going to talk about that. And the reality is you are just going to have to memorize this table, which is on our, it's on the graphical organizer for this unit. Okay, so base geometries are kind of if there are just atoms attached. And lone pairs do weird things, and I'll tell you about that in a little bit. Okay, and I'll kind of run through those. So if 4 things are attached, the base geometry is tetrahedral. And I'll often have you draw these structures, okay, just for practice, because this actually does take a lot of practice, and you have to kind of picture this stuff in your mind. And in order to kind of go from what you see here and connect it to what you see here, I'm going to kind of run through one, and I'm going to tell you. So the fundamental problem here is we're talking 3 dimensions. So we have to kind of figure out a way where we can draw this thing in 3 dimensions. So what I like to do is I put 3 atoms, this atom here, and this atom here, in the plane of the screen. Okay, or on the plane of your paper. And we just draw those as normal. So those have 109 degree angles. So let me go back and let me draw that. Okay, and I'm going to use this sort of generic E and X, or you could use A and B. It doesn't really matter as long as you know what you're talking about, okay? And the reason that I'm going to do this is because this structure doesn't have 4 things attached to it. So I've got a bond coming up, and I've got a bond going down at about 109 degrees. Okay? Now, these other 2 are actually a little difficult because this one is actually going back, is actually going back from the plane of the board that these 3 are in. And this one is actually coming out. So the way that, come on, rotate back. The way that I do this is by, let me get this oriented correctly again, okay, is we use wedges, okay? And a solid wedge like this means that this is coming out of the plane, okay? And then we use a dashed wedge for something going back into the plane, okay? So this is a tetrahedral shape, and you should be picturing this stuff in your head as you do this. And we'll be making models of these things, and you'll get practice with this, because this is actually a little tricky, and it's good to have an idea in your head. But notice that that looks a lot like this tetrahedral shape, okay? So that's the base, if there were only other atoms attached. But in NH3, there isn't. So this is not actually the correct structure. But I have you do this because it's good practice. Okay? So now I need to go back and I need to add the lone pairs. And it's good to do this in a very consistent way. So find a place that makes sense to you, and then always draw these the same way. So I like to put a little, I like to put my lone pairs here, and then these are H's now. And now I can put my elements back in. So that's an H, here's an H, coming out of that dash, that wedge, that solid wedge, and then there's the dash wedge with another H. Okay. So if I go back to my drawing here, and I remove a bond, and I add a lone pair, now we only name, when we're doing these names, we only name the bonds. And if you look at this, this looks like a little short, squat, 3-sided pyramid, okay? And it's 3-sided, so we call it Trigonal Pyramidal. Okay, so this is a trigonal pyramidal. Sometimes I call it pyramid or pyramidal. It doesn't really matter. Okay, trigonal pyramidal. Now, let me go back to this real quick, and let me take this lone pair out. Okay, and put a bond back in. Okay, so this is called tetrahedral because it makes a 4-sided figure. Okay, here's one side down here. Here's another side connecting those 3 atoms. Here's another side connecting those 3 atoms. So that's 3, and then there's another one connecting those 3 atoms. That's 4. Okay. If I put a lone pair in, okay, now this is still telling me that the bond angles are 109 degrees. Now the problem is, as is sort of diagrammed here, a lone pair actually takes up more space than a bonded pair, okay? So a lone pair will actually push everything away from it ever so slightly, okay? So I have to go to ClF3. Nope, that's not right. NH3. Here's our molecule, NH3. Okay, and as you see, the bond angles are actually a little less than 109.5. Okay, I don't need you to know that that is the case. It's just less than 109. Okay. So that is making a Vesper structure. Now, I would highly recommend watching the video that I make on memorizing the shape types, okay?